Hello everyone, it's July the 20th. Okay, let's see if we can handle both today. Try this one first. Reverse linked list. That's an old problem. Give a head and two integers, left and right, where left is smaller than right. Reverse the nodes of the list from position left to position right, and then return the reversed list. Okay. Well, the naive way is always to count, but we don't want to count. I remember there should be a way to we just count the number, right? So it's left or right. So this is 2 to 4. 1, 2, 3, 4. So 2 to 4. So we just go 1, go that much, and the other go that much. So that's basically the head, right? And then we can do our swap. It's fine, just regular swap. Not regular swap, regular inverse. We will do a temp, and then this one will be pointing here. Wait, how do we do reverse? Yeah, we can actually point. This one can point to none, right? And then this one we point to another thing. And then basically we just do a reverse of this. But I forgot how to do reverse. So the next pointing back, right? And then move this forward. Yeah, this one pointing back. And then we move this forward, and this one pointing back, move this forward. So we have current, previous, and current. Okay, previous and current. And we basically say not really, previous, current, right? Previous and current. And then we say this pointing back, and current become here, previous become here, right? And then we just all pointing back, and this one also pointing here. So eventually this one will be pointing back, and the next one will be none. And then what we do is this to next, and this to next equals this thing, and this next equals this thing. Okay. I feel this is just some edge cases we need to deal with. Dummy equals list node next equals head. Well, we have a dummy. And then left node and a right node. Node equals head. Left node. While left node equals left node on next. Left minus equal 1. Maybe not, because initially this is 1, right? So 2 is actually just a move on one side, so it should be while left minus 1. And if it's 1, then we don't do. And if it's 2, then we basically move once. Right, so that's that. And then we do the same thing to get a right node, and this will be right, right node. Okay. So we have this one. We call that the remain shall be right node on next. Okay. So now we're just gonna reverse from left node to right node. Actually, I'm gonna say right node on next set to none. So now we're just gonna reverse it from left node. So what do we call? We say who's pointing to the left node? Good point. Upstream. Up. Yep. Down. Okay. So now we can say current and pre, right? And we say temp is equal to current on next, okay? And then current dot next equals pre, so we're pointing back, which is fine. And then, okay, so we say pre-current equals up and L node, right? So while current temp equals current on next, and current on next equals pre, right? So current on next equals pre, and pre equals current equals current equals temp. Right, pre equals current equals temp. So current is here. And then, well, current, say current, next, this is the temp. Current on next equals pre equals current, and current equals temp. Okay? And then, well, current on next, that will be none. Temp will be none. And current on next, pointing to pre. Yes, pre equals to current equals none. And then, well, we jump out. So when we jump out, the pre pointing to the last one, right? The pre pointing to the last one. So when we jump out, we can just say up dot next equal to pre, because pre pointing to this. Current, we don't really have to. Current is pointing to none. And then we need this. Ooh, we have to do this first. My bad. Up dot next. Up dot next equals to. No. What did you do, man? Up dot next, right? Up dot next equal to down. So up dot next, this one dot next equal to down, and up dot next equal to pre, right? I want to return dummy dot next. Okay. We might not be right, so we have to run some test cases. Of course, the given test cases. Oh, we should run both. Okay, seems to be right. That's already the edge case. Well, actually, it's not the edge case. Here is how we do the edge case. 1 to 5. 1 to 1. 5 to 5. I think that covers all the edge cases. Okay, seem to be good. Yep. Oh, What the heck? So this is the third time. This is by myself. This is just last year we had this. And then this is basically this time. I only checked the previous method. So pretty much it is correct, right? So it was correct. I mean, what you can say is maybe we don't have to do this. We just keep counting. Okay, you want to try that? So like instead of, so we get a left and we don't do this, so not while current, we basically do right. So we need to know from this how many more. Okay, can try that. Additional travel should be right minus left. Right here, 2. So from here, 1, 2. So that's additional. And we don't need to do this. Don't have this, don't have this. While additional, blah, 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 additional minus equal 1. Hold on. Okay, addition minus equal 1. So we go temp equals current on next, so temp is here, right? Current out here is a pre, and then current equals temp. And now we count addition 1, right? And the next one, current, temp is here, and current equals temp. Now it is 0. Now it's 0. That's not enough. So we need to go plus 1. Do one more step. And then current will be here. Right? Current will be here. And pre will be here. Okay? And okay. Then up dot next will be current. And up, and yeah, this one pointing back, and then up dot next up tree. This might be right as well, and then I think this one is better. I'll try it. Yep. There we go. So we save some time on only doing one traversal. We only need to do one pass. First, we reach the left node. Then we compute. Then we perform the normal linked list reversal operation, but instead of checking whether we have reached the end of the list, we count how many steps have been taken. We should take right minus left plus 1 number of steps for the reversal operation starting from the left node. And the only other trick is to use a dummy node at the front. ON. I'm pretty sure this is how this method 32 helper. What? True left node. Oh, what the heck is this? Is this using recursion to do reversal? Nah. Yeah, this is slow, I know, but this is pretty fast. What does the solution say? Oh, it's recursion. I'm not doing recursion on this. Iterative, yeah, I like that. Yeah, doesn't matter. Doesn't matter what method. This is good enough. Okay, so we deal with this. Oof. Yep, I realized that too. Aha, you can use a for loop. That is true. Oh yeah, okay. Additional setup is not necessary. For loop will be sufficient. Yep. Okay. Alright, let's take a look. If we can solve it, good. If not, yeah, that's fine. As the ruler of a kingdom, you have an army of wizards at your command, okay? You're given a zero-indexed array strength, where strength I denotes the strength of the ith wizard. For a contiguous group of wizards, wizard's strength form a subarray of strength. The total strength is defined as the product of the following two values: the strength of the weakest wizard and the total of all the individual strengths of wizards in the group. Return the sum of the total strengths of all contiguous groups of wizards. Ooh. So we have 1312 has a total strength of, oh, it is a subarray is 1. So 1312, 1331, 12. So we do 1 plus 1 times 4 is 1 times 3. 3, 1, 1, 2. And 131 is 1 times 5. 3, 1, 2. And then 1, 3, 1, 2. Holy guacamole. How long? It's 10 to the 5th. I mean, if you just go through everything, it's O(n) squared. That's not too big a deal. Well, I mean, you can also, if you have a prefix sum, then the sum operation will be easier for you to do because we are doing a sum, right? So what we need is a prefix sum and a prefix minimum. How do you do prefix minimum? Like, given a range, we want to know the minimum immediately. And in this case, it just so happens, except from these individuals, it's always a 1. And then it's the sum, right? I mean, I know all of them, so I can sum them up. That's O(n). Starting from here, it's O(n) again. Dude, man. Ten to the fifth, you cannot O(n) squared. How can we solve this smartly? 1, 3, 1, 2. That's 3 times 3. So we want 4, 5, 7, right? So 1 times 4, 1 times 5, 1 times 7, starting from 1. Sums on 3, 3 times 3, then 3 times 3, and then 1 times this, that's 4. Then do this, 1 times 6. And this, 1 times 1, that's 3. 1 times 3. And then 2 times 2. Okay, is there any restrictions on this? No restrictions. Jeez. DP? I don't try DP. Well, how would you do DP? Let's say if we know the strength of these, because we will have to know the strength of these no matter what, right? Because 1, 3, 1 is something we need to know. Let's say we know all the strength of this. How does that help if we add one more? Well, so we know all the strength this, then we need to include this, right? And the way to include this is, well, we add this by itself, and then include this, this, and this, right? And this, what we have is the sum of the total sum of this. If we have the total sum of this, which is the smallest times something plus smallest times something plus smallest times something, right? Now we need to include one more. So for each of those, that ending in 1, that's the only thing we cared about, right? Ending in 1. Maybe it should be all the strengths that ending in 1. Okay, so basically it's 1, 3, 1, 1, 3, and 1, 3, 1. The sum of these. So you have 1 times 1, 1 times 1 plus 3, and then 1 times 1 plus 3 plus 1. So we have this, right? And if this value is the smallest, right, then it can be write as 1 times 1 plus 1 plus 3 plus 1 plus 3 plus 1. That's the current value. Now we have 2. Now we introduce 2, then everything ends in 2 is going to be 1, 2, 3, 1, 2, and 1, 3, 1, 2. And it involves 1. So smallest is still 1. So what we do is just add 2 to everything, right? So for 2, what we're going to have is just we're going to say we have a 2 and we have a 1, basically, because this is like everything, so it's 3, so 2 times 3, right? Because we have add 2, add 2, add 2, 2 times 3 plus whatever the previous one. So that's for 2, so 2 end up with this. So the next thing comes up. So if I just have this list of things, right? So next thing comes up. If the next thing, if the new value is the smallest value, right? If the new value is, it doesn't really matter. The new value might be, you might have something might be smaller. So, but the new value comes in, right? So the previous value can say that it has 1 based, right? 1 based have all these, 2 based have some, 3 based has some, but all of them are starting from this one. So now I have the new value comes in. If the new value is the smallest, then everything will base on the new value, right? Everything will base on the new value. So what this means is, because it's 1 based, it is 1 times all these things, 2 times all these things. So 1 times all these things is just all of those things, right? And then for me adding to it, I just need to add I feel like I'm there, okay? I feel like I'm there. We just need to form a better argument. So what I'm talking about is we can have 1 base. So like from this, right? We say this to this, it's not 1 base. This to this, not 1 base. This to this is 1 base. So if it's 1 base, it's going to be this to this, this to this, this to this, right? So we have this plus this plus this plus this, all these things plus together. That's 1 based. So if I come in now, then I need to know the 1 based, how many, right? How many is 1 based? How many is 2 based, right? How many is everything based? So it has to be more than just a sum. We also need the base, the number, right? So when we come in, it has to go from here when it reach 1, right? So from here, 1, 2, 3, 4, 5, we have this, 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 this. So I have to add it 1 time, 2 times, 3 times. I've added those that many times. We have to add, so it'd be this times, so I have to add 2 times this number, right? And that will be 1 based and doesn't change. And it's 2 based, so everything's that. Now, so this is handling if I am not the smallest. So I have something in this that's smaller than me. Then I just fit that, right? Everything, I just fit that. Okay. That's one situation. Oh, but you still have to go through all those numbers. Like this list can grow, right? This list can grow. If you have a small one, then you actually don't grow. We'll see later. So now if you're big, and that's what happens, you're big, and you have to add yourself as well. Right, now we only consider those smaller, right? Yeah, so what if I am small, right? There's something smaller than me. What if I have something that's the same, right? If I come in as a 3, and previous has a 3, right? Previous has a 3. So if I have a, wait, what's the limit? 1, right? So if we have a 1, at a certain point, if we have a 1, then that 1 is going to rule everything to the left, right? But we have something that's not reaching a 1, okay? So it's like from here, that's like 1, right? And then you come here, which just means like 1 will handle like this much, and that's the second value can handle this much. So when you come in, if it's smaller, it's done. If you're the same, so what I'm saying is when you come in as a new, you just do 1, right? And next one come in, if that thing is smaller than you, right? Then your count need to upgrade, right? Your count need to upgrade. And one counter will be upgraded as well because we. What do we upgrade? The number. No. The count is from 1 to there. That's the count, right? From a value to the one that's smaller than me. That is the count. So when we come in, we have this value. And if there's something bigger, right? If the next one is bigger, I'll look into this dictionary. I am bigger than everybody. If I'm bigger than everybody, then those things do not change, right? Because they're smaller. They still rule everything to the left. I'm bigger, but I can rule from me to the next smallest, right? Because if a smaller one comes in, it's gonna rule them all. All right? If you think about it, if I have a 1, which is the smallest, and if 1 comes in, whatever's in the past, they're gonna be ruled, right? So if 1 comes in, it's just going to be the current index, and we are going to because 1 we add a 1, right? And then 1 to whatever is previous. So previous, let's say it's ruled by some value, okay? And the whole model from here, right? Let's why don't we use this example, right? 1, 3, 1. So right now is 1, okay? And we say at the first position, we say we have a 1 point to count as 1, value is 1, okay? Now 3 comes in. 3 comes in, look to my left 1, and we try to see all that's smaller than me, right? All that's smaller than me that ends in 1, right? All that is smaller than me that ruled by those smaller than me that ends in 1. So when I come in, then I have to add myself to it. So, but I don't, so I add myself first, 3, right? And then I have 1, and the result is 3 because I ruled myself. And then for everything that's smaller than me, I don't change the number that's being ruled because it's just 1, right? And I will have to add myself to it. What do you mean by add myself to it? I say the previous we have 1, so now I have 3, so I have to add myself to all those 1. So 1 plus 3 is 3. So everything and add 3, like everything, all including 3, right? Including 3. So it's just that number. It doesn't include everything that starting from 1 is everything starting from 3. So however many starting from 1, so all of those, I have a sum, right? Because it's starting from 1, so all of those will have a sum. And then that sum need to add, so it'll be 1 plus 3, that'll be 4. Add 3 times 1, okay? Next one, we have a 1. Again, we're gonna, so when 1 comes in, we probably need a binary search. And binary search, we find that something in the past has ended in, like when ended in 3, we have something that's ruled by 1, right? Now I have 1 come in, and 1 is smaller than 3. So all those ruled by 3 will be ruled by 1, right? Well, what do you mean? Like we have a path, if a certain path, right? So we have all these paths ruled by some smallest values, right? Doesn't matter, we have all these ruled by smallest values. And now when I come in, if I am smaller, then I will take over, right? So for everything that is smaller than me, they will belong to me, right? So for everything that's larger than me, for everything that is equal to me, and they also transfer transfer the ownership, right? Because I will include more, right? So what are you saying? So let's say here, it rules that many, 1, 2, 3, 4, right? Because this and this, so just 1, 2, 3, 4, it owns that much. And then when I comes in, all of these owned by me, right? So what we're gonna do is from this going up, like the same, I'm going to bigger, they're gonna own by me. So everybody that's bigger than me, right? The number of counts is going to be determined by me, right? The number of counts is determined by me, which is my current count, my index. And we just say index is 1, right? 1, 2, 3. It's going to be 3, right? And then the sum is going to be the previous plus how many and times myself plus the previous how many times myself, and of course plus myself times myself. Okay, so this will come to 8. All right, this will come to 8. It rules 3, and it comes with 8. And that's because 1 is, now if I am, this is everything that's bigger than me, and if everything's smaller than me, I rely on them. I don't change, and then I just add to them. Okay. And the next one is 2. So 2, looking previous is 1, which is smaller than me, so I can occupy myself. 1 and 2. And then I have to do the previous. So I also don't change how much I can do. So it's going to be 3. And 3 times 2 plus 8, which is equal to 14. Okay, now we're going to calculate the total. Total is just the ruler times the sum. So it's 1 times 1 plus 3 times 3 plus 1 times 4 plus 1 times 8 plus 2 times 2 plus 1 times 14. Let's see if they come up to 1 plus 9 plus 4 plus 8 plus 4 plus 14. 40. We're missing 4. Okay, I feel like this is promising. We'll just see where do we miss. So let's see, 1 is 1, right? And 3, ending at 3. 3 by itself. 3 times 3 is 9, yes. And we have this thing, which is 1 times 4. That's correct. Here we have 1 by itself. I have 1, 3, right? So I have 1 by itself. I have 1, 3, which is 4, and a 1, 3, 1, which is 5. So here shall be 10. But I have 8, so we have some issue here. So again, 3. So I am smaller, so whatever is 3, I want to say 1 times 1 plus 3. Oh, hold on. Yes, 1 times 1 plus 3 plus 1 times 1 plus 3 plus 1 times 1 plus 4. 2 plus 3 plus 1 plus 4. How did I come up with 8? That's 10. Oh, some arithmetic issue. 1 times 1 plus 3, that's 1 plus that's 4. 4 plus 4 is, now 1 times 1 is 1. So it's whole. 1 plus 3 plus 1 plus 4. That becomes 9. Are we having 9? 1, 4, 5. Should be 10. Oh, and itself. My bad. 1 plus 1 times plus 3 plus 1 plus 1 plus 4 and plus 1 times 1. That's 1, 2, 3. That's 10. Okay, yes. And the last one is 2. So we do 2 by itself. That's 1 and 2. And then for the 1, I don't change, so it's those 3. So it's going to be 10 plus 3 times 2. So that's 16. Okay, 16. So I'm going to change a little bit here. So this is going to be 1 times 10 and 2 times 2 and 1 times 16. Yes, I see the addition. 44. Yes, we have a method. Well, whether this is going to time out or not, this is not sure. But definitely, we will, if it's smaller, then we will wipe out everything. If it's bigger, if it's increasing, like as long as we have something small, right, we'll wipe out everything. Like everything will be condensed into one. But I'm afraid is every time we come in, we have something bigger, something bigger, like 1, 2, 3, 4, 5, 6, 7, like that. And when that happens, this method, each one you will have to add 1 more. Each one you have to add 1 more, right? And when you add 1 more, you binary search, you find everybody is smaller than you. Then you have to go from the first one all the way update to the last one. Now that is the thing that troubles. Which I think that will cause us to time out. Unless they don't have this way of input. If it's strictly, like if it's increasing, right? If it's increasing, like if I am bigger than you, right? Is it possible that yeah, if I'm bigger than you, I will maintain you, and then I'll add my value to your count, right? Add my value to your count, add my value to your count, add my value to your count. And all of them will be 1. Yeah, that is a problem. Okay, so let's try it, okay? And if it time out, at least we know that this solution will work. Now, usually, if we're talking about interview, this is good enough most of the time. They will ask you to, figure out if it's possible to make it faster. And you say yes, but you don't know how, and you need some hint. And this will be different from a situation where you don't give any solution. And this is our solution, and we have a solution, which I think is valid, right? And we only need to keep 1, right? So we just say, call it dp is going to be a dictionary with strength 0, and we're going to call, it's going to be two values, which is 1 and strength 0. Okay, because we have length is 1, so this is valid. Then we'll say for I in range 1 to length strength. Okay, and we'll also have res equal to 0, res equal to strength 0 by itself. Okay, so for each one come out, we're gonna, we have to go through everything. So there's no point to binary search. We just go from front to the end, and anything that's called temp equal to strength I. Might as well use this mutable 1 and the strength I. Right? So this is the initial state, and then we're gonna go through the previous, and we say for key v in dp items. Okay, we say if the key is larger or equal to strength I, if it's larger or equal to strength I, which means I would take over, right? Then I say, let's call current equals strength I. So I don't have to write the strength I so many times. I got sick of it. All right, if it's larger equal to current, then we say temp current the count. What you're gonna do with the count? So we count if I have something that's bigger than me, right? What do you mean something that's bigger than you? If it's smaller, they'll wipe out. So bigger than me must be here, right? This is bigger than me. So whatever that, like count, let's say it counts for 1, 2, and then when I come in, I'll count for 1, I'll count for 2. So I say 0, right, plus equal to v0, I increment my count, and current 1 is the sum because they belong to me. Then all of the sum, like from this to this, plus this to this, plus this to this, like all of these sum will plus equal to v1, right? We have to v1 plus what? Plus v0 times current, right? And whatever we have back then, plus how many, and then I'll add myself to it. So that's if I am larger than, then they basically go this. Else, if not, if k is smaller than my current, then I do not dictate. Then I say k, right, equal to v0, like I don't change the count, but I will change the value because this plus v0 times current, right? Because I add that much. And then once we're done, we say dp is equal to temp. What about the rest? And rest, so we have to go through everything, right? Now we say for kv in dp.items, because I updated, right? I say rest plus equal to k times v0. No, v1. v0 is count, k times this, right? And then eventually we return rest. Yeah, I think this one will time out. Well, if we time out, we call it a day, and I might try to think about this during my sleep. If something come out of it, perfect. If not, then we'll look at the hints. 214, 213. Man, this is an interesting one. Total strength. Let's see if it works. Oh, it worked for the first one, doesn't work for the second one. Why not? All right, let's print dp. You know what? No, I want to see the dp here. Print current and dp. Okay, so if 4 have 2, right? Because 4 by itself and 4 5, and then the sum is 13. That's interesting. How is that 13? Five is a 5, right? And then 4, I say I'll take 5, so it'll be 9. Oh, 9 plus 4, yeah, and itself. So I have 2 with 4 and 4, 5. 4 and then 4 plus 5. Okay, that's good. 6 is bigger, so we have to do 6, which is this, yes. And we still have 4 with 2, and then 2 times 6, so everything has to add 6 to it, which is 13 plus 12 is 25. Okay. So in total, this times strength 0. There we go. Now it makes sense. Okay. Yeah. Oh, easy to generate test case though. Oh, terrible way of generating test case. Ten to the 9th. Oh. Yeah, but 10 to the 5th. Yeah, I think we can try. How do you do 10 to the 5th? We just say list range from 1 to 10 to the 1 to 10 to the 5th plus 1. I can't even print it out. This is useless. I don't even think I can. Can I select you? Ah, Lord. Okay, 1, 2, 3. Okay. No. Why do you cat it? This is what we want, right? Can this text box even hold? Oh, damn, it can. It's impressive. All right. 10 to the 5th. It's going to time out, pretty sure. Yeah. It's just basically O(n) squared. Yeah. It's gonna time out, but it's fine. We can at least have some record, right? Have some record down, and then try to think if there's any smarter way to do this. I'm pretty sure the test case will be exactly the same. Yeah, it's good. I mean, even if it times out. Yes, exactly. That's exactly what I was afraid of. Yes. Yes. Yes, 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 yes. They have exactly the idea. It's the same test case, so we know. But let's see. On another side, we just see if this is like the last one, then we can probably. Oh shoot! It's not even the last one. So the downside of this problem, of this approach, is if we have an increasing streak, then we are significantly hampered. But we might be able to calculate those separately. So what I mean by that is if I have a stretch which is increasing, right? 1, 2, 3, 4. Everything can only be by itself. What you're saying? It's not everything only by itself. Like if we go for the front, it will have to rely on the one in front of me, right? So can we compute this fast? Like I can just, if I'm on upstream, right? I just compute whatever it is, because all I need, remember, all I need is the last value, right? The last value. And if we are on, so basically we go up, right? It's just going to be up and down, up and down, up and down. And every time we go down, we consolidate, right? Because every time we go down, we consolidate everything, and then everything in the front, we'll have to figure out how to handle the things in front. Well, we'll think about it later. Yeah, it's not a simple problem. O(n) squared TLE. That's okay. That's okay. Okay, end up right here. I'll see you guys tomorrow. Adios.